let's gaze upon this very old etching and see what's really happening in this case. You have some people reading, you have some people feeding the fire, you have a still, you have some alembics, you have somebody grinding something up in a mortar and pestle, you have fire. There's a lot going on in this picture. This is a portrait of a distillation lab, and probably, most likely, these people are distilling alcohol. So they're taking fermented mash and they are distilling it in these alembics to try to collect, let's say this again. They are distilling a big mixture of something and it is collecting into these alembics and they're collecting alcohol, okay? So this is a very ancient technique that you're going to learn about, and it was really started to make alcohol for consumption. So I just want to show you what happens in the preparation of spirits. There are plenty of people who distill in their own homes, although I don't recommend it, it's a little dangerous. But what happens here is you take some sort of raw material and you grind it up into a meal, and this is usually some kind of grain or plant or potato, and what you do is mash it up and you allow it to break down, and then you add yeast to it. And so all the sugars that have come out of this grain or potato or plant, those have leached out sugars as the starch has broken down, and yeast is going in there and it is chewing up those sugars and it's producing CO2 and it's producing ethanol. And there are other elements that come with the plant, with the potato, with the wheat, with the pine, with there's so many different, sources of this alcohol. And so those elements that come from that particular source are going to instill some of their own flavors. Those are called congeners. So imagine you have this mash, you have this wine, beer, mead, chung, brew, whatever you want to call it, and you want to make it stronger. So what are you going to do? You're going to distill. How does distillation work? So that big thing that was in the center of the image previously, that was the still. What happens here? So you have that fermented mass, and it contains alcohol, grains, water, congeners, those things that impart their specific flavors, like what makes agave gives tequila its flavor. So those things are heated up in this central still, and the alcohol, because it has a lower boiling point than the liquid in there, the water, the alcohol is going to reach its boiling point and it's going to start to vaporize. And those vapors from the alcohol are going to rise up and they're going to reach that tapered neck, and they're going to start to reach a portion where there's no heat anymore. And that's when they will reach that alembic collection device that's cool, and those vapors will condense into a liquid. Okay, and this is distillation. So we won't go on to the aging and the blending process. I wanted to get you to the distillation, but what did we do here? We separated alcohol from a complex mixture on the basis of its boiling point being lower than the boiling point of water. Welcome to distillation. So here we have some videos that can be really helpful. These are going to show you what is going on with distillation. Notice we have cold water pumping through the condenser, and it's constantly being recycled. And in this case, we have lavender flowers mixed with water, and they are boiling. And that was the end of our video. So in this case, what happened here is that let me get back to my original presentation. What we had here was vapors rising, reaching that cool area where water was recycling, and then we were starting to collect until the subscription came up. So let's look at another video. So here we have a simple distillation being set up, and we have some liquid mixture, and we have a boiling stone in there, and we're starting to heat up that liquid mixture. And what's happening is, as it's heating, vapors are starting to rise where the analyst is pointing. We have a thermometer. We have the bulb of the thermometer positioned right beneath the sidearm, and then those vapors are going to reach the thermometer and indicate the boiling point. So we want to take the temperature of those vapors, and now the vapors are reaching the condenser, which is the cool area where we want the vapors to condense. The vapors are going to travel through the condenser, convert to liquid, and collect in our collection flask. And as you can see here, those liquid drops are collecting. Okay, so this is our simple distillation. Now let's look at another type of distillation. This is fractional distillation. So you'll notice that there's an area in the heating element. There is another piece of glassware that has been added, and that is what makes this a fractional distillation. So this is our fractionating column that they're showing you right now. And they're insulating it because they want it to stay nice and warm. And what's going to happen is just the same as before with the simple distillation. You're going to have your vapors rise up, reach the thermometer, and that will indicate the boiling point of that liquid that has now converted to vapor. The vapor will travel through the condenser, and it will start to collect in your collection flask. So fractional distillation is going to take a little bit longer because you have the fractionating head. But because you have that additional surface area with more what's called theoretical plates, you're going to introduce a better separation than you would have in simple distillation. So I will leave this video for now. You can definitely watch it on your own time. But that is a good primer for your distillation. And when you watch the first link, you can see a little bit more detail if you keep refreshing the page. So let's jump into boiling point. So we already talked about melting point. Boiling point is a very similar idea, but it has to do with the conversion of a liquid to a gas. So boiling point, or BP, is the temperature where vapor pressure of liquid phase becomes equal to atmospheric pressure. Okay, so for water at 1 atmosphere, the boiling point is 100 degrees. Now, if we change our external pressure, we're going to change the boiling point. I just want you to be aware of that. So remember that melting point should be used for solids, and boiling point should be used for liquids. Okay, so distillation is a type of technique that allows us to separate components of a mixture based on their boiling point. So it relies on the fact that different components of a mixture will boil and vaporize at different temperatures. Okay? This is how we can actually, for example, separate ethanol from water, because ethanol and water have different boiling points. So ethanol, if you boil up a mixture of water and ethanol, ethanol is going to boil first because it has a lower boiling point. And it will allow us to, with this apparatus that I showed you in the videos, allow us to separate the ethanol. What happens in this experiment is that you have a 60 milliliter mixture of methanol, which boils at 64 degrees, and water, which boils at 100 degrees, okay? And what you want to do is to distill these and then figure out how much methanol was actually in the solution, okay? So figure out how much methanol and how much water was in the solution. And you would be conducting both simple and fractional distillation and comparing data for both. Now, I want you to understand that methanol and water can be fully separated from each other. That is, they do not form what's called an azeotrope. So they behave as an ideal solution that follows Raoult's law. We'll get into that, and I also urge you to read about it in your Pavia techniques. So methanol and water are separable via distillation. So normally this experiment would be worked in pairs, and one of you would perform simple distillation and the other would perform fractional distillation. So you would each have your 60 ml methanol solution, and you would set up separate apparatuses, and then you would collect 15 milliliters of distillate. So that is the liquid that has boiled off and condensed, okay? You will collect 15 total mils of distillate, and the point is that you want to record the temperature of every mil of distillate that is collected, and that will enable you to determine how much of it is methanol and how much of it is water. So for both distillations, you will graph the volume of distillate collected versus temperature. What is the difference between simple and fractional? Well, I showed you in the video the apparatus was different. Now, how can we utilize these two techniques? Simple distillation is the purification of a liquid that contains non-volatile impurities. So volatile means that something has a low boiling point or a high vapor pressure. So it can go from liquid to gas very easily. So for example, in perfumes, you have volatile molecules that once the perfume is sprayed on somebody's body, those molecules are going to come off the body as a gas and then reach our nose and reach our olfactory nerves, and it allow us to smell sensation of rose or citrus or whatever in the perfume. So keep in mind what volatile means. Non-volatile impurities are going to be things like salts. A non-volatile impurity is something that doesn't have a low boiling point, okay? So how can we utilize simple distillation? We could purify seawater for drinking, for example, by distilling off the water and separating it from the salts. Another good use of simple distillation is to separate mixture of liquids where the boiling point difference between those two liquids is very large, over 100 degrees Celsius. Now for fractional distillation is best utilized when the difference in boiling point is much closer. So here it says a difference of greater than or equal to 30 degrees Celsius. Okay, so which distillation would be better for us to separate methanol and water? You saw that the difference of boiling point in methanol and water was around 36 degrees. So fractional distillation is going to be better for us in this case. So we go into this experiment assuming that fractional distillation is going to give us a better separation. We want to actually do the experiment and plot the data and see if that's true or not. So here's what the apparatus looks like for simple distillation. If it was difficult to see in the video, it's a lot more clear here. We're going to have a heating element, so that's our heating mantle, and we're going to have liquid in our distilling flask, and you're going to have a boiling stone. Now, I drew in the boiling stone for you. The boiling stone is there to enable even heating inside the mixture of liquids. So what happens is it prevents any bumping of the liquid, and it also ensures that there's even heating going on. Okay? And so then you'll notice that you have a distilling head. That is, the distilling head has this side arm on it. And we have the thermometer adapter to enable us to put a thermometer inside. And we have the bulb of the thermometer is positioned in a very specific area. You see that it is right below the side arm of the distilling head. Very crucial for you to get the accurate boiling point of the liquid as it starts to vaporize. So what happens here is now those vapors are going to travel through the apparatus, and once they reach the condenser's purpose is to cool the vapors and turn them into liquid. So imagine we have all these vapor particles, and eventually they're going to start to form little drops of liquid, and then they will collect here, and then we're going to get distillation happening. So we've separated off the first low boiling point liquid in our receiving flask. Okay, so I also want you to notice one more thing about the condenser. The condenser is connected to these two water sources, okay? So, well, one water source. We have water going in, so this is cold water going in. This is connected to the sink. And that water is going to circulate from the bottom up, and it's going to come out and go into the sink. Okay, so the water in is connected to the faucet, the water out is connected to the sink. So you constantly have a supply of fresh cold water going through the outer jacket of the condenser. Okay, so you'll notice this condenser has two layers. There's an outer jacket and then there's an inner tube where the vapor is going to go through. So the vapor never comes into contact with water because you're separated by a glass wall. Okay, so this condenser serves the purpose of converting vapor into liquid, or condensing it, hence the name. So here is our simple distillation apparatus. Now, when you would set this up in the laboratory, you would have to clamp this glass apparatus where the clamps are indicated to you. Now, if you had to set this up in the laboratory, this takes some time to set up. For those of you doing simple distillation, it would probably take more time to set up the apparatus than to actually conduct the experiment. Here's fractional distillation, okay? So we're also going to have a heating element, which is not indicated here. Okay, so we have heating mantle. Now, you have your distilling flask, you have a boiling stone again, and you're going to have this fractional distillation column. So this is a condenser that doesn't have water in it, but it has been stuffed with some material. So you see this material here in the hollow part of the condenser. That is to provide more surface area for the vapors. And this is the very important part of the fractionating head, because what this does is it creates more surface area to allow multiple vaporization and condensation cycles. So those cycles are going to go up, 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 up slowly. So vaporization, condensation, vaporization, condensation, vaporization, until the vapors reach the thermometer. Okay, and again, you have that specific placement of the thermometer bulb right below the sidearm of the distilling head. You again have your condenser, water going in the bottom and out the top. So you constantly have cold water circulating. Those vapors are going to convert to liquid, and the liquid is going to collect here, okay? So just having this part right here is what makes this a fractional distillation, okay? So where the simple distillation has one theoretical plate or one vaporization condensation cycle, the fractional distillation has several vaporization condensation cycles. And that's what makes fractional distillation much slower, but much better at separating two liquids with different boiling points. So here we have some graphical data, and we we're just showing you how to determine percent composition. So remember that you start off with 60 mils total volume of methanol and water of some unknown composition. And so what we have to do after you start the distillation is collect your distillate in a graduated cylinder so that you can say every mil what the temperature is. So x-axis is volume, y-axis is temperature. And what the student has done here, they've collected 5 mils at approximately 64 degrees. Now, the rest of the 15 mils, the 10 mils that they've collected, notice what's happened. The temperature has shot up to 100 degrees, and that has been water. Now, we've only distilled 15 mils. We didn't distill 60 mils. So we have to extrapolate this curve and understand that all the methanol is gone, so any remaining liquid after 15 mils is still going to be water. So how do we figure out percent composition? We're going to look at the methanol is the first one. We collected 5 mils out of a total 60. That, and we multiply by 100, that is going to be around 8% methanol. Now, we collected 55 mils because remember, the remaining, all the methanol, after 5 mils of methanol has come off, all the remaining 55 mils are going to be water. So 55 mils at 100 degrees Celsius over 60 times 100 gives us 92%. So the percent composition of this solution is 8% methanol and 92% water.